Well, good morning to everyone. I think it's time to start. It's 11:15. So I'm going to share my screen now. Okay. So you can see the schedule of this second part of the mini symposium with the title Fictitious Domain Methods and Applications.
Enrique, we cannot see your screen sharing.
Oh no.
Did you click the green?
I have to press share
Yeah.
button. Okay. Now.
Perfect.
Okay.
Now we can see your desktop. So if you can open the PowerPoint presentation. There you go. Perfect.
Okay. Well, here you can you can see the PowerPoint of the schedule of this of this mini symposium with the title Fictitious Domain Methods and Applications. We have 5 talks, and I'm going to introduce each one of the speakers between the videos. So the first speaker is Héctor Navarro. He is one of our PhD students with Professor Rodenas and me here in Valencia. And he's going to speak about how to deal with the stabilization of the discontinuous Galerkin formulation within the Cartesian grid finite element method. Now, Héctor, the floor is yours. So the video. And I stop sharing.
Hello everyone, my name is Héctor Navarro Garcia and I'm going to present the work with title The Stabilization of the Discontinuous Galerkin Formulation within the Cartesian Grid Finite Element Method. This research has been carried out under the supervision of Professor Rubén Sevilla, Enrique Nadal and Juan José Roda. The final goal of the PhD thesis test framing this contribution is to develop a mathematical framework that let us accurately simulate the propagation of waves through a medium in time domain. The electromagnetic scattering problem is a problem of great interest for naval and military industry, among others, that lies within this context. The physical phenomenon is governed by Maxwell equations, which are an example of hyperbolic system of partial differential equations. The special features of this kind of equation must be considered to properly design the computational algorithm. The finite difference method was the first method that allowed to obtain an approximate solution for the scattering problem in arbitrary domain, and it remains at the mode with the spread numerical tooling hinges. A range of more sophisticated alternatives have been proposed to overcome the limitation of the finite method. The use of high-order finite element methods with discontinuous Galerkin formulation is probably the most promising approach. However, the generation of high-order curved meshes is an unsolved problem that prevents from its spreading. We propose to implement the high-order DG approach within the framework of the Cartesian grid finite element method. This way, the mesh generation process will no longer depend on the geometry of the problem or the order used to approximate the solution. In CGDG, we use another approach. What characterizes the DG formulation is that every node is attached to a single element, even those that lie on internal edges of the mesh. As a consequence, the solution is element-wise continuous, and the global continuity is satisfied in weak form by applying numerical fluxes through the edges of the element. The input of the mesh generation process in CGFEM is the computational domain. The first step is to embed it in an easy-to-mesh square domain called bounding box. Next, we obtain a preliminary mesh by splitting the bounding box into a set of smaller square subdomains through an iterative process. Then we intersect the mesh and the geometry. The element that completely lies outside the computational domain are removed. The remaining element classifies into internal elements that are treated as standard superparametric elements and intersected element that split into a set of cells that fit geometry for integration purposes. The analysis mesh is used to define the approximate solution, while the integration mesh let us appropriately capture the geometry. Here we present some advantages and drawbacks of the CGDG method. The key aspect we need to overcome in order to make possible the practical use of the proposed scheme is the dependence of the maximum stable time step on the mesh geometry intersection. The portion of an element inside the computational domain in CGDG may be arbitrarily small. Following the workflow presented in the slide, we notice that element 3 has very little support and that the degrees of freedom associated to the node on the right only affect the solution within the computational domain. In our case, this cut pattern also negatively affects the stability of the time-advanced algorithm. We propose an stabilization strategy that solves this limitation. It applies when the mesh geometry intersection have been computed. Using a geometry parameter such as the relative portion of the element in the computational domain, we can identify the element that may behave badly. The integration cells linked to an element classified as unstable are reassigned to an adjacent element. Rearranging the integration cell modifies the support of the interpolation functions. The support of the shape functions associated to the unstable element vanish, and the degrees of freedom that cause instability can be removed from the system of equations. The weak form of the operator computes as usual, and it is important to remark that this stabilization strategy do not have any effect on the DG formulation of the problem of the implementation of the time integration. We continue this presentation showing some numerical results. We study the scattering of a perfect electric conductor cylinder whose diameter is equal to 8 times the wavelength of the incident field. We use quite a coarse discretization of 12 nodes per wavelength and approximate the solution by this wave polynomial distribution of order. Circular domains pose a challenge as they usually lead to bad cut patterns. Starting with the initial mesh presented in here, we identify these bad cut patterns that may lead to unstable behavior. Applying the reassignment strategy, we get rid of this unstable element and degrees of freedom, and we obtain an stable discretization that does not suffer from instability or conditioning issues. Here we present the third component of the magnetic field and the static scattering width. As you see, our numerical solution for the scattering width perfectly matches the analytical solution. Thank you very much for watching.
Thanks, Hector, for your video. Now, next speaker is Professor Rodenas. Well, he was my PhD supervisor in Valencia, and we're still collaborating in developing one of the fictitious methods that are currently well in the literature. So he's going to speak the H-adaptive mesh refinement for topology optimization in the framework of the Cartesian grid finite element method. Please, you can continue with the video. Thanks.
Hello, I'm going to present the work H-adaptive mesh refinement for topology optimization in the framework of the Cartesian grid finite element method developed by my colleagues David Muñoz, José Albelda, myself, Juan José Rodenas, and Enrique Nadal at the Polytechnical University of Valencia in Spain. The CIMNE method, developed by Benson and CIMNE, is one of the most commonly used topology optimization techniques for structural problems. We will find a couple of problems. We have a lack of geometrical definition along the new boundaries, and the solution accuracy is not taken into account. So this can lead to unfeasible solutions in, for example, volume minimization with stress constraints. So the objective of this work is to solve these issues using mesh refinement techniques in the Cartesian grid finite element method framework, CGFEM. This is the outline of the presentation. After the motivation and the objectives shown in the previous slide, I'm going to present now a reference problem that is going to be used to test the proposed refinement strategies, and I finish my presentation with numerical example. The reference problem. This is a cross-section of the reference problem for these loading conditions. The analytical solution is going to take the form of a cylinder subjected to an internal pressure, for which we are going to have the exact values of the displacement and the stress field. With them, we are able to evaluate the optimal radius that allow us to satisfy this constraint. If we run the topology optimization problem, we will obtain something like this. If we smooth the relative densities field, we obtain this solution, where the blue lines represent curves of the same relative density. The green line will represent the optimal radius, the optimal analytical radius. So if we represent the relative density along one of the radius, we obtain this curve. Here we have the optimal analytical radius, and we see that the external boundary is defined in a wide region, too wide. Then we are going to propose 3 different refinement strategies to solve this problem. We are first going to present a voxel integration strategy, then a density-based refinement, and an error-based refinement strategy. In the standard formulation, we use a single value of relative density in each of the elements. What we propose is to split the elements into integrations of domains. In each of them, we are going to have a different relative density value and a different sensitivity of the solution. So what we obtain is that at the cost of the original mesh, we are going to have a resolution of the size of the, related to the size of the integrations of domains, like this. What we obtain is a narrow area where we define the external boundary. We also propose a density-based refinement. The idea is to start the iteration to minimize the compliance with a uniform mesh. When the process is starting to converge, we stop it, and we refine the elements that are having intermediate values of relative density. We continue the process, stop it again, obtain the solution, and repeat the process. The final solution, as we realize, is having a very sharp definition of the boundary. If we use this strategy in the reference problem, this is the solution that we will obtain. We see that we have reduced the diffuse zone, but we have not been able to capture the optimal analytical solution represented by the green curve, because the stresses evaluated in this area are not accurately evaluated because the discretization is too coarse. So we also propose to use error estimation techniques to reduce the size of the elements where appropriate. If we do that, we obtain a mesh that is also refined in this region, where we were having higher error values. And as you see, as we are evaluating the right values of stresses here, we are going to capture the optimal analytical solution. I will conclude the presentation showing 2 numerical examples. This is the first problem is a hook with a load here, and we want to keep the von Mises stresses below 2. We run the topology optimization process. We get this solution. This is a pictorial representation of the solution, and here is the evaluation of the von Mises stresses that are always below 2. The last example is optimization of a dental implant, where the CIMNE model of the bone has been directly obtained from the medical image, and where we have considered frictional contact between implant and bone. This is the mesh used for the analysis, and this is a representation of the implant. Thank you very much.
Thank you, Juanjo, for the presentation. Please don't you forget to post your questions in the chat. Well, next speaker is Gianluigi Rosa. He's a full professor in numerical analysis and scientific computing at CISA Lab. Now his talk is going to speak about advances in model order reduction for fluid structure interaction problems. Please go ahead.
Good morning. I am Gianluigi Rozza. I'm going to talk about model order reduction for fluid structure interaction problem. This is a joint talk with Monica Nonino and Francesco Ballari. I will not focus a lot on model order reduction, but I will just tell that this is a very important topic, also with a growing demand for industrial and clinical research project. with also some technology portability with offline, online computing. The topic of the main topic of this brief introduction will be on fluid structure interaction problem, and I would like to recall the ALE formulation, arbitrary Lagrangian Eulerian formulation, in order to describe time-dependent domain for fluids in blue and for structure in red. So the correction on the, as you can see here, of the Navier-Stokes equation, guaranteeing the continuity of the geometry, the continuity of the velocity, and the balance of the stresses between pressure and structural part. The problem is a slow convergence for the reduced order methodology when we have transport dominated problems. So with Professor Yvonne Madet, we have recalled a methodology that is going to introduce a transformation, so a pre-processing on the solution manifold in order to reduce and to have a faster decay of the Kolmogorov and width, and to reduce the dimension of the reduced basis methodology. So we do a transformation thanks to this pre-processing in order to guarantee, let's say, a faster convergence also of the POD. To do that, we can introduce several examples. One is a rotating cylinder, and we are just going to map a physical map of the Karman vortex, such that we keep it in the horizontal position, also when this vortex is rotating with time dependency. This is helping us in enhancing the decay of the Kolmogorov and width and of our POD, and so we can reduce the dimension of the reduced basis in order to have better computational performances online. So this can be done also for the time-dependent problem, also in presence of some parameter, for example, the Reynolds number. So we have checked the same methodology, the same procedure for different Reynolds number, and we can see that we can enhance and improve the computational performance also of this methodology with the parameter. The further step is to reintroduce this for fluid structure interaction problem and to have some automatic way to generate the physical transformation mapping for the pre-processing. And this is an example in fluid structure interaction where we have in red the structural part and then we have in blue the fluid part. Here we can see that what we are going to map our the pressure snapshot, so the pressure wave propagating inside this channel, and we are going to map this such that all the peak of the pressure will be in the middle of this channel. To do that, in order to enhance this physical transformation, we are going to introduce also some interpolation technique, and in order to save computational cost. Here we can see that also the pressure recovery with this pre-processing is enhanced, and also the energy recovery in the system with the pre-process pressure is behaving better compared with the classical POD approach. Of course, we have also to stabilize our problem using a supermiser, and then we have also in the online computation of the pressure to pull back this solution. Here we have some comparison between the reduced and the full order solution for the pressure, and also for the displacement, and an accurate pressure is guaranteeing us an accurate coupling with the structural part, and so also an accurate computation of the displacement. And also here we can see that the performance, thanks to this pre-processing, also online are better because we have better accuracy and we have lower relative error for the dotted line representing our pre-process solution. And just to conclude and thanking you for the attention, I acknowledge the European Research Council.
Many thanks, Professor Rosa, for sharing this video. Well, next talk is given by Guglielmo Scovazzi. He is a professor at Duke University, and he's going to speak about a weighted shifted boundary method for free surface flows. Please go ahead.
My name is Guglielmo Scovazzi, and I'm going to talk about a weighted shifted boundary method for free surface flows. Collaborators on this work are Oriol Colomès, Alex Main, Leo Nouveau, which at the time were working under my supervision at Duke University, and currently Oriol is a professor at Delft University of Technology. Alex Main is a research scientist at ANSYS, and Leo Nouveau is a professor at the University of Rennes in France. In 2018, Alex Main and I proposed the shifted boundary method as a new unfitted finite element method to tackle the challenge of complex geometry in engineering applications. We showed in a paper that the shifted boundary approach is a viable strategy for complex geometry Navier-Stokes calculations, which can be achieved with very, very short setup times on relatively large grids. When considering the key ideas of the shifted boundary method, as I said, it is an unfitted approach. We use Nietzsche's method to impose boundary conditions weakly, and we apply boundary conditions on a surrogate boundary near the true boundary. So as you can see here, we define the surrogate boundary as gamma tilde, and this surrogate boundary is in proximity of the true boundary gamma, and we have a distance vector d that measures this distance. The idea of the shifted boundary approach is to appropriately modify the boundary condition to account for the discrepancy between the surrogate and the true boundary by means of Taylor expansions. So the idea is that on the surrogate boundary, we can extrapolate the solution to the true boundary, and so we can fundamentally perturb the boundary condition G that is now applied on the surrogate boundary as G tilde, where we subtract the first term in the Taylor expansion. Now, of course, higher order terms can be included in this approach. When considering moving boundary problems, one of the examples are free surface flows, in which a traction boundary condition is applied on a moving free surface. Now, the challenge here is that moving boundaries have not been yet tested with the shifted boundary method, and when we performed earlier calculations with the traditional shifted boundary approach, we observed large oscillations in time of the pressure variable. This is a known issue in immersed boundary methods that do not preserve accurately the total volume of active fluid in the calculation. We were able to find a modification of the shifted boundary approach, which actually solves this issue. And the key idea that I don't have the time to describe here in detail, but I am delivering a 20-minute presentation with all the details. The key idea I was saying is to weight the variational formulation with the elemental volume fraction of the fluid. Using this approach and developing the variational equations, we were able to drastically reduce pressure oscillation, if not completely removed. In the longer presentation that I'm going to deliver at this conference, we will go into full details about the various problems that can be solved with the shifted boundary method. I would like to acknowledge support from PK's award and ONR and point you to a reference that we recently published on this approach. Thank you very much.
Thank you, Professor Escovazzi. Well, now we have our last speaker, Giulia Sambarato. She's a PhD student from Bordeaux University since 2019. So as you know, the fictitious domain method also can be called, or sometimes you can find in literature as immersed boundary method. So in this case, I guess that Giulia is a fully immersed COVID-19 PhD student. So she started just at the end of, just at the beginning of the pandemic. So she's going to speak about a projection-based model reduction methods for nonlinear mechanics with internal variables, application to thermohydromechanical systems. So go ahead with the video, Giulia.
Welcome to my presentation. I'm Giulia Sambataro and I'm a PhD student in the University of Bordeaux. My presentation is on model order reduction for THM problems. The physical problem that motivates my research work is the one of storage of radioactive waste materials in geological means. This problem is described by large systems coupling mechanics, hydraulics, and heat transfer problems. THM systems model the behavior of temperature, pore water pressure, and solid displacement in the neighborhood of geological repositories, which consist of many boreholes located deep underground that are responsible for the thermal flux. The THM systems can be reconduced to a general mathematical form in terms of residuals associated to equilibrium equations and functions representing constitutive laws. They link state variables U to internal physical variables W, and they are both parameter dependent. Here in equation 2 there is the high fidelity element-based discretization of the residuals. Numerical simulation of system 1 is challenging due to nonlinearity, the presence of internal variables, and a large number of parameters. We adapted and extended the methodology, relying on a projection-based model order reduction. For the training step, we choose an adaptive sampling, implementing a POD greedy algorithm with a residual-based error indicator. In the online phase, to reduce assembling costs, we apply the hyperreduction technique based on empirical quadrature procedure. This technique requires integration only over properly selected grid elements. The performance of the developed reduced order model with empirical quadrature is first of all validated in a solution reproduction case. Here, the percentage of selected grid elements is shown for different choices of an empirical quadrature tolerance. Also, the decrease of the error is depicted for the same tolerance values with respect to increasing dimensions of the approximation space. Now, moving to the parametric case, how to select training parameters. Here, the POD greedy algorithm convergence history is illustrated, so the error indicator with respect to training parameters indices. At each iteration, the selected parameter that maximizes the error indicator is marked in black. Going on in green, you can see the previously selected parameters. Also, the dimension of the updated reduced space is reported. But what happens in terms of predictions? Here, a numerical result in the out-of-sample case. The maximum out-of-sample error is computed for each parameter in a test set. Values are computed for several dimensions of the reduced space that is updated at each iteration of the training algorithm. These errors are compared to the prediction errors found through a strong greedy algorithm. Thank you for the attention.
Well, I would like to thank all the speakers for their contribution. Now, well, in the chat, you can see that there are some questions, and I would like you to answer. First question, in order of time, is to Juanjo. So from Frederick Larsson, do you define the stress constraints point-wise? If so, have you encountered problems with the mesh-dependent stress concentrators? And do you need to consider that explicitly in the age refinement strategy? The microphone, Juanjo.
Can you hear me now? Hello? Yeah, thanks for the question, Frederick. Yes, we do consider point-wise stress constraints. What we assume now is that we are having problems with smooth solutions, not having singularities. And what we also do is that we consider the stress constraints over a recovered stress field that we evaluate. So this avoids problems. And what we also do is that, as I mentioned in the presentation, we refine the mesh according to error estimation criterion, so that finally we are having accurate stresses on the boundaries. So as far as the numerical examples that we have been running is concerned, the process is running nicely. And we are working now in a procedure to take into account that that we could also have singularities, and we are working on a process to solve this. Did I answer the question?
It seems you did. So
okay.
we go for the second question from Alexei Luthinsky to Juanjo Rodenas. Do you need stabilization on bad liquid cells? If yes, what is the stabilization?
Okay, let me share my screen. Just a second. 1 second, please. Share screen. There it goes. I suppose, no. No, sorry. The answer is yes. We use stabilization techniques. For example, we will be having an issue here because this element is having a very low contribution to the energy of the system. So even large variation on the displacement of this node, or even this node or this node, will have almost no effect here, and the problem, we will have problems. So we need to stabilize the displacement here. So what we use is a recover displacement field evaluated on these nodes that could be producing the problems. And this has the effect of including a stiffness here. So with this technique, we avoid this kind of problem, stabilization problem. I hope I answered the question.
Thanks, Juanjo, for the answering.
Thank
Well,
you.
now I have a question. So it's a question that is not previously with not in agreement with Juanjo. So in the last example, in the dental implant, are the stresses along the contact area playing an important role?
Are the stresses along the
contact area? So
along
who
the area?
Who are they calculated in this case?
Yeah, well, we evaluate, we solve the contact problem between the bone and the implant, right? And yes, this will have an influence in the implant. The only thing is that in this case, we enforce the outer layer of the implant to be kept, so we cannot have holes on the outer layer of the implant. In that sense, it will not have many problems in the definition of the topology of the implant. It will have problems in the remodelation process. That is something that is being studied in our group as well. The remodelation of the bone remodeling.
Okay, thank you, Juanjo. Thank you very much for your answers. So next question is addressed to Hector from Ahmed Sherif. Thanks for the presentation. I have a question, the same question as Ruben to me. What do you do for representing curved interface input elements, and how do you get the high order integration quadrature?
Okay. Do you hear me?
Yeah.
Okay. Thank you, Enrique, and thank you, Ahmed, for your question. Well, first of all, I'd like to apologize for the volume of my video. I hope you can hear it. Well, moving to the question of Ahmed, well, I will share my screen to explain. Okay. Do you hear me? Do you see my screen now? Okay. Here you see how we capture the curve interfaces in our CAD element. We consider the exact definition of the geometry provided by the CAD. So we obtain the intersections of the CAD with our mesh, and then to consider the exact representation of the geometry, we use NFM integration strategies. So we are putting our integration points on the curves in 2D to compute the quantities on the boundaries, and when we need to obtain the quadratures on the physical domain inside an element, we first need to define these cells we use for integration purposes, and then we consider the surface integrals and project it to the node that it's not on the surface. And the number of integration points we use is more or less the same that for for the element, but in itself. So in integration in cat element, we have far more integration points, but they are very few compared to the total number of elements. So that's it. I hope I have answered your question. If not, we can explain it in more detail.
Well, thank you, Hector, for your answer. Now we are moving for the question to the next speaker, for Gianluigi Rozza. So the first question is from Professor Rodenas. So in the abstract, you mentioned that you use CUTFEM for fluid structure interaction, but then in the presentation, if I'm not wrong, you do not mention CUTFEM. Could you mention about the implementation with CUTFEM and the main difficulties you faced?
Thank you for the question. So in the presentation, I focus more on the reduced order modeling part and on the pressure stabilization for the coupling in order to get accurate results also for the structural part. For the full order, we can use, of course, classical finite element approaches, Taylor-Wood and so on, but we are using also a CUTFEM approach, which was quite interesting in terms of their potential use, because we were able to stabilize the reduced order modeling part of the CUTFEM with the classical approaches based on the supermiser. The only problem for this is that we have a slow convergence in the POD, because we have a slow decay of the Kolmogorov width, and this is the reason why we decided to introduce in the reduced order part, especially in the online part, this physical transformation on the snapshot, a pre-processing, in order to enhance the convergence and to reduce the dimension of the online reduced basis.
Thank you, Gianluigi, for your answer. So now you have another question from Ahmed. So how do you stabilize the pressure? Do you use numerical stabilization for the force transfer to the structure?
What we found as a good compromise in terms of efficiency and computational performances is the stabilization used thanks to the supermiser technique. So we are enriching the velocity spaces. The velocity spaces will be enriched with some additional velocity snapshot, and these velocity snapshots are coming from the solution of a supermiser problem. In this sense, we are fulfilling an equivalent in super condition at the online level, at the reduced level, with depending on the parameter. But we are able to improve the accuracy of the reduced pressure. The pressure sometimes is converging, but with the supermiser, we have a better accuracy. And this better accuracy is transferred to the structural part, thanks to the fact that we are guaranteeing the continuity in the velocity, in the geometry, and the continuity of stresses. So for us, this has been a good compromise in terms of performances and in terms of accuracy for these non-linear couplings. But of course, there are other options that could be used.
Thanks, Gianluigi, for the answers. So next, I have a question. This is from my production, I said, and is, well, from my ignorance, because I'm not familiar with fluid structure interaction. So which is the physical idea behind the reduction of the end width you mentioned in your presentation?
Yeah. Heuristically, we reducing these, there is, let's say, we can associate, roughly speaking, to the decay of the convergence of the POD. But reducing the Kolmogorov width, it means that we are able to build very efficient reduced basis approximation spaces with a limited number of basis functions. So having very small Kolmogorov width, it means that we are able to generate very efficient and very good reduced basis approximation spaces. The problem is that when we have a transport dominated problem, or when we have other problem characterized by, for example, multi-physics, multi-phases, interfaces, and so on. So when physics is getting quite involved, if we are not able to have a very good reduction in the Kolmogorov width, the dimension of the reduced basis is increasing a lot. And then we are somehow not able to have very good online computational performances. So being able to control and to have a fast decay on the Kolmogorov width means that we have computational efficiency, and it means that we have possibility to introduce a model order reduction in our problem, which is effective. Otherwise, we risk that this is not the case, and this is just a very good numerical exercise, but without the goal of the reduction in terms of computational efforts.
Thank you very much, Gianluigi, for your answer.
Thanks to you.
Enrique, your microphone is...
Sorry. Next question is to Guillermo, and is from Professor Rodenas. So one major drawback of the fictitious domain method is that imposing boundary conditions is far more complex than in the standard finite element method. Hence, the need to use Nietzsche's method or other. But you say that you still use Nietzsche's method to impose boundary conditions weakly. So I do not quite understand what do we gain with the shifted boundary approach. Is that we do not need to special integration technique?
Yes. So thank you very much for the organizers for the invitation on the mini symposium. Yes, to answer the question, in the shifted boundary method, we do not have cut cells. So you just integrate on full cell or full edges of the grid. And this has the advantage that you don't need to use special integration techniques. In addition, when at least the original version in which we don't, for fixed boundaries, we also don't need to apply any special stabilizations for the small cut cell problem, because there are no cut cells. So these are the two main advantages of the method. You hear me?
Yes, it was frozen for a while.
Oh, sorry, it was frozen for a moment.
Yeah.
But basically my I was able to. Did you hear my reply, or I was just frozen?
No, we can listen to you, but the video is not working smoothly.
Ah, okay. So
perhaps you can stop the video. I don't know.
Yeah, maybe I stopped the video. Okay. So to answer the first question, can you hear me better now?
Yes.
Okay. So the two main advantages of the shifted boundary method are related to the fact that we do not compute on cut cells. Therefore, there is no integration on cut cells required. So there is no special integration rules that we need to apply. Also, when there are no moving boundaries, so if we have applied the shifted boundary approach also to solid mechanics problems and other problems in fluid mechanics in which the boundaries don't move. So in this case, basically, there is no need also of stabilization of the small cut cell problems because there are no small cut cells. So this fundamentally are the two advantages of the method. Can you, did you hear me okay, or there was still a problem?
Yes, now it's fine. Thank you, Guillermo. So we go for the next question to you from Ahmed. You mentioned the known problem of having oscillation in pressure when the fluid volume is not exactly conserved. I'm having the same issue with XADG method, second presentation of protection session today. My question is, do you think there is a solution for that issue?
Yes, I think that what we basically, because of the lack of time, I was just able to present the results without the details of how we obtained them. At the end of my presentation, there is a link, a reference that if you're interested, you can read. The idea is the following: that let's say in a method typical of immersed grid, an unfitted method, one needs to be aware of the fact that if we have moving boundaries, these boundaries are activating and deactivating degrees of freedom in the calculation. If we have incompressibility constraints, so if in addition to the momentum equation, we have an incompressibility constraint, fundamentally, if you activate more degrees of freedom or less, the incompressibility constraint discretely changes form, because you're applying over more, you're basically testing over more test functions than associated with the new degrees of freedom and that have been created. As a result, the constant pressure mode that is associated with the volume preservation may be affected. And so we don't observe oscillations in space. The oscillations occur in time because the average pressure changes if we don't have a good preservation of the total volume in the calculation. In our work, we found that it's not necessary to have the preservation exactly. It's not necessary to have an exact preservation of the total volume in the calculation. It is sufficient that the accuracy to which the total volume is preserved is of the same order of the overall accuracy of the method. So if you are using, in our case, a quadratically convergent finite element method, we need to have that this error in conservation needs to be quadratic. So once we balanced that, we saw a drastic reduction of the oscillation, if not a complete disappearance.
Okay, thank you. So go for your last question. So what is the current status of treating Neumann boundary conditions in shifted boundary method? In particular, in free surface problem, you have to approximate both Dirichlet and Neumann in some way. I will look up the details in the full talk, but thanks in advance for general idea.
Yes. So for problem, so in the formulation we are using for fluids that I presented today, we are using a stabilized method in which the pressure is piecewise linear. It's a piecewise linear field, and then we apply canonical variational multi-scale stabilization, SUPG type stabilization. So because the pressure is linear, and because the problems of interest in our group with these free surfaces do not require highly accurate viscous stresses at the surface of at the interface of the free surface, then we could simply use a Taylor expansion on the pressure, and that was sufficient to retain high level of accuracies for the many tests we performed. Clearly, a method of this type, if you're interested in studying the formation of waves in the ocean, in which the shear of the wind produces eventually the wave, this approach that is purely based on a pressure Taylor expansion will not give you good results. We recently have a recently accepted paper on solid mechanics in which we treat the Neumann boundary condition using mixed formulation, which is written only on the layer of elements attached to the surrogate boundary. So we have a way basically to very stably reconstruct nodal approximation for gradients and meaning of stresses, and we use those to impose Neumann type conditions. Thank you.
Okay, thank you, Guillermo. So we are running out of time. Well, it remains 7 minutes. So, and we have the questions for the last speaker, for Julia. So there is one question from Pedro Diaz. It says, you use POD greedy algorithm. Can you elaborate it further? Is the greedy part including redundant terms that the POD suppresses? I think there are some problems, perhaps. Julia?
Sorry, can you hear?
Yeah. Yes, no.
Now, yes?
Yeah.
Okay, sorry, thanks. Okay, maybe I can briefly share my screen, just a minute.
Sure.
Okay, so answering to the question, no, it's slightly different. I go into detail just a minute. So you have the algorithm that starts with a training set that I decided with a certain variation from reference values of the parameters. You start with empty spaces for the reduced for the approximation space, and you start with a certain configuration, a certain vector of parameters. Then what you do is solving the full order model to have snapshots. I have a time-dependent problem, so you will have snapshots in different time steps. Then there is the data compression that is done to enrich and enlarge the reduced space, and I don't go into details too much, but here the aim is not to store all the snapshots and to enlarge the reduced space only using the last computed snapshots. About the error indicator, you have here this for loop in which I compute the error indicator for each parameter in the training set, and then the one that performs that maximizes the error indicator is selected. So answering to the question is a bit different because as you can see in the data compression step, we have snapshots in different time steps, while here in the error indicator step, only we are talking about parameters. So the one that maximizes the error indicator is selected and then is put in the selected parameter set, and the full solver is performed here. I don't know if I answered the question.
Yes, it seems that Pedro say that he has clear, the question is clear. So I have a small question to you. Is just from my curiosity. So what are, I know that the presentation is just 5 minutes, the video. So could you give some details about the physics of your problem, the problem you are resolving, the THM problem?
Yes, you are right. There were no details about the physical problems because I tried to generalize it to have a general mathematical formulation. But in a few words, I could say I have the equilibrium of forces for the mechanical viewpoint. Then I have the conservation of water mass as for hydraulics, and then the energy balance, and all these three physical phenomena are linked together, and I also linked to constitutive laws that describe the behavior of the system when the radioactive waste is stocked deep underground in the soil. And so it's I think a complex phenomenon that links these three physical parts, so the mechanics, hydraulics, and heat transfer.
Okay, thank you, Julia. Now it's more clear for me. So we are running out of time. It only lasts 1 minute for the session. I had one question asked to all the speakers to make a debate, but I think we are running out of time. So I will comment the question, but discussion will be, I don't know, next time we meet. So what are, in your opinion, the limitations and or challenges for this kind of fictitious domain method? So I think it's something to think about in the future, perhaps for next time we meet. I hope physically anywhere. So it's something to think about, not to discuss now. Well, now I would like to thank all the contributions in this mini symposium. We're very happy with all the contributions, high quality contributions. And now if I can share the screen, I have the instructions to say that we are meeting again. I think I'm sharing the screen now. So we are meeting after lunch at 13:30 for the next session, mesh and model activity. Okay. Many thanks for your contribution, and see you all next time. Thank you very much.
Thank you very much.
Thank you. Goodbye.
Goodbye.
Bye.
Thank you.